Okay, it's a great pleasure to have Dibyendu visiting us for the last few days. Dibyendu did his PhD in University of Maryland with Chris Czerzinski, and he was working on Maxwell's demons, trying to understand microscopic models of Maxwell's demons. So after that, he was in Boulder, Colorado, trying to understand the atmosphere, I think, and El Nino and so on. And now he's in UC Berkeley, again trying to understand, I think, maybe biological systems using non-equilibrium statistical physics. So today he's talking on modeling Maxwell's demons.
Okay. First, thank you, Abhishek, for inviting me here and giving the opportunity to present my work. And also, you may have noticed that the topic of the following talk is somewhat different from the main theme of the current discussion meeting. I hope that's not a problem. In fact, I hope that it acts as a refreshment, okay, this little diversion. Okay. So before we go into the talk proper, let's start with a curious observation. Okay. Let's start with the following question. How much thermal energy is contained in 1 liter of ordinary air? Okay. Now, the ordinary air of volume 1 liter, it weighs less than a small coin. So you would think the energy content, the thermal energy content should be very less. However, if we do the calculations, we can show that this small amount of air has sufficient energy to toss 7 kilogram bowling ball or any object 3 meters off the ground. Now, that's a lot of energy for 1 liter of ordinary air. And the immediate reaction I had after doing this calculation is the following. If such a small amount of air can have such an immense amount of energy, can't this amount of energy be used to solve our energy crisis, at least partially? That's the idea that got us interested in such problems. But how will we do that? A particular solution was proposed by Maxwell, not having this particular problem in mind, but no doubt he did propose a solution in this direction. So in 1867, he proposed a thought experiment where he considered a chamber full of gas, and the chamber is separated into 2 halves by a partition in the middle. And in the partition, there is a small hole with an intelligent, neat-fingered being in front of the hole. Okay. This intelligent being, which we will refer to as the demon, can do the following. It can make measurements of the gas molecules that comes towards the hole and measure their position and velocity. Furthermore, it can operate a trap door on the hole. So it can close or open the hole at will. What it does is the following. Whenever a fast molecule from the right tries to go towards the left through that hole, it will open the trap door so that the fast molecule can go towards the left. However, if a slow molecule tries to do that, it will close the door so that the slow molecules cannot go from right to the left. Similarly, whenever a slow molecule tries to go from left to the right, it will let it go. So it's just the opposite, but it will not let go the faster molecule. Okay. So if it goes on doing this, what happens after a while? We'll see that the slower molecules will gradually accumulate on the right, and faster molecules will gradually accumulate on the left. Okay. Note that we haven't done any work or anything. We have just simply separated the molecules, the fastest from the slower ones. But now, the left half has become hotter compared to the right half, which is now colder, and hence I can use that thermal gradient to drive a heat current from left to the right, and I can convert part of it into work. Okay. And at the end of that operation, I can bring everything back to the original condition, and in this way, I have started with a chamber of gas with certain thermal energy, extracted part of its energy and converted into work. So that could serve as a possible way to extract work from the atmosphere. Okay. Yeah.
So you're assuming making observations and
exactly.
the trap door doesn't cost energy.
Yeah. So, well, there was some debate about that because Brillouin, for example, he tried to argue that measurement itself should incur some energetic cost. But later, I think Charles Bennett, and we heard his name in the last talk, so he pointed out via a counter example that we can have situations where measurement does not cost energetically. So in that sense, we can take the ideal limit where we do not incur any energetic cost for the measurements. That's frictionless. Again, I mean, these are the idealizations we should assume for this conceptual experiment. So we assume that the door is massless and there is no friction, and hence there is no energetic penalty there. Yeah. Okay. But that should have ringed a warning bell, right? Because what are we doing at the end of the day? We started with a single heat source, we extracted energy out of it and converted into work. But that is exactly in opposition to the second law of thermodynamics, which says that we cannot devise any process whose sole effect is to extract energy from a single heat source and convert into work. That's the Kelvin-Planck statement of the second law. So in a way, we seem to have violated a sacred law. Then what do? We have two options. Either the setup that we have talked about works, and in that case we have to wonder what happens to the status of the second law. Does it mean that the second law doesn't apply all the time? And if so, what are the situations when it doesn't apply? On the other hand, if we believe in the second law and say that this type of contraption cannot work, we have to find out why it cannot work. Okay? And it's precisely these questions that has led to discussions for more than 100 years without any apparent solution. And only in 1960s, through the works of Landauer, Oliver Penrose, and Charles Bennett, a resolution has come into play. And the resolution is neatly encoded in the so-called Landauer's principle, which says that to erase a certain amount of information, there is an energetic penalty. In particular, if we want to erase one bit of information, one has to dissipate at least kT log 2 amount of heat into the reservoir. Here T is the temperature of the reservoir and K is the Boltzmann constant. Okay. So how does it apply to our previous situation? People argued along the following line. To operate, the daemon has to make measurements about the position and the velocities of the molecules, which means it is gathering information which is being written to its memory. Okay. Now, after a while, the memory will become full, and hence it has to erase its memory before it can operate any further. But whenever it tries to erase that memory, it has to dissipate at least this amount of energy. And this is more than the amount of energy it extracted before to perform any work. And hence, at the end of the day, if we try to go back to the original condition where its memory has been reset, we haven't violated the second law, because we have actually dissipated more in general than with what we extracted before. Okay. Now, there is another way of saying that thing, and that's the following. So whenever we write information on a blank memory device, we increase its entropy. Okay. And because the daemon increases the entropy of its memory, it is allowed to decrease the entropy somewhere else. And that's why we saw that apparent violation of the second law. And the Landauer principle says that if we want to erase the memory, then there is a decrease in the entropy of the memory, but that cannot happen unless we increase the memory somewhere else, and that's why we have to dissipate the heat to increase the entropy in the reservoir. Okay. Now, from this discussion, you might get the idea that all these discussions are in terms of generic principles or heuristic ideas. We do not have any concrete example to look at. Yeah, please. It's just a Shannon entropy actually. We'll define it, but it's a Shannon entropy, the information entropy. So, okay, in these two lines, I refer only to the memory, and by memory, you should keep in mind the hard disks or any memory element that we have here. And for any such memory element, you can define the Shannon entropy, right, for each bit. And by entropy, I mean that Shannon entropy here. Okay. So we do not have any concrete example to hold on to. We do not have a picture as to how this thing is happening. And that was true until very recently, even though we have spent like more than 150 years of discussion behind this problem. Okay. So, in the following, my goal is to give an exactly solvable and analytically tractable system for which we know everything that is there to know, which acts like Maxwell's demon. Okay. Furthermore, we want the system to be autonomous in the sense that once we start the system, we do not want to intervene in its evolution, or we do not want to have an external thermodynamics force which can drive a current from one point to another. Okay. And we want that because sometime in the future, we do want to make an instrument which operates according to this principle, and we do not want to tinker with that instrument. Once we initiate it, it should do the work on its own. Okay. And once we do so, we will discuss the implications of the second law along the principle of Landauer's eraser in more detail corresponding to that particular system. Okay. First, let us have an overview of the model, and this is the schematic picture of the model. It has three components, something called the daemon, and this is this three-state system, and I will come back to it. And then there are bits, which are basically two-state systems where I can encode information. And finally, there has to be a mass which I can raise to perform some work. And all these components are immersed in a heat bath of temperature capital T. And this is the picture you should have in mind. And in the following, I will take these components one by one and discuss their details. Okay. First, let us talk about the daemon. The daemon is a three-state system, the three states being A, B, and C. It can make thermal transitions among these states, however, with a restriction. It can make transitions between A and B and C, however, on its own, it cannot make any transition between A and C. Okay. Which means, if I leave it alone without any bits or anything else surrounding it, then it cannot make any complete rotation on its own. It will get stuck either in state A or in state C. Okay. Now, let us talk about the bits. As I said, the bits are two-state systems. I will call the states to be 0 or 1, and I denote the bits by this arrow. So, if the arrow points towards 0, it is state 0, and if it points towards 1, I will call it state 1. Yeah. Okay, good question. I should have been careful. So, all the energies of these three states are the same, and I can assume that the energies are 0. Okay, but if you can make a transition from A to B and from B to C, then why can't you go in 2 steps from A to C? Right. So, one has to think of these as transitions between metastable states of some complex molecule, for example. Okay. Now, whenever there is a transition, the rate is determined not only by the energies, but also an effective free energy barrier between the states. And one might think that the free energy barrier between these two states is so high that within the experimental time scale, such transitions do not take place. Yeah, it can go from A to C via B, but not directly. That is what I meant. Yeah. That is another possibility. Yeah. That is another possibility, right. Thanks for the question, because here too I assume that the energies are the same, and still they cannot make transitions because of a very high free energy barrier between them. Okay. Or you might think the Hamiltonian is disconnected, so that there is no cross terms. Okay. Now, I let them interact, the daemon and the bit, and the daemon acts something like an enzyme for the bits. So, in absence of the daemon, the bits cannot make transitions from 0 to 1 or vice versa. However, in presence of the daemon, the bit can go from 0 to 1. However, just like in enzymatic reactions, the daemon also has to make a transition, and in this case, I assume that that transition is from C to A. Okay. So, in summary, if the bit has to go from 0 to 1, the daemon has to simultaneously go from C to A, and the reverse transitions are also possible. The bit can flip from state 1 to state 0, but simultaneously the daemon has to go from state A to state C. Okay? So, that is the interaction between the two systems. Directly. So, these transitions are direct, because through B it can do on its own, but to go directly it has to be assisted by the bit. That is what I meant. So, the transitions along these dotted lines, they have to be mediated via transitions of the bits. Yeah. Otherwise, it can go from A to C via B. That is already allowed, as we discussed. So, you can think that transitions along the continuous lines are allowed without any problem. Transitions along the dotted lines have to be assisted, in the sense that they can happen only if simultaneously there are transitions in the bits. That should be the picture we should have in mind. Okay. And these are like enzymatic reactions, that there are very many reactions for which time scale is very large. However, if we put the enzyme, the reaction becomes very fast, because it finds alternate pathways. And the idea we are proposing here is along the same line.
So, there is an effective lowering of the free energy.
Exactly. There is an alternate pathway for which the barrier is low, and hence it can go through that pathway. Exactly. Yeah. Yeah. Okay. And we are not happy with just one bit. We want many, many bits, and we already had this picture before. So, what we want is a stream of bits, okay, and they are uncorrelated. I assume that for the ease of analysis, and P naught denotes the proportion of zeros in the incoming bits, and P1 the proportion of ones. Okay. And the daemon interacts with only one of them at a time. So, the daemon interacts with the nearest bit. And finally, the separation between the bits is constant, let us call it D, and we can assume that the bits are embedded on a tape which moves slowly towards the right with certain velocity v. As a result of which, the daemon interacts with each bit for a fixed time interval. I call it tau, and that is simply the separation over the velocity.
So, you are Maxwell modeling the molecules of the gas molecules?
No, these are not gas molecules. Yeah, gas molecules provide the heat path, and that's the only thing they do. Yeah.
Excuse me. Your system is energy is conserved or not?
Well, there are thermal fluctuations because the whole system is embedded in a heat bath.
Sorry, your whole system is composed daemon and memory and heat burst itself.
Yeah, if you take the whole system, yes, total energy will be conserved.
Okay,
Yeah.
yeah. Yes, I'm asking your viewpoint is a microcanonical point of view or a canonical point of view, which one?
You might think it's canonical point of view.
Okay.
Yeah,
So
yeah.
temperature is fixed, but the memory and daemon's energy is not fixed, right?
Good question, but I just said that the energies of the different states are the same. So, the system can fluctuate among the states, like the daemon can fluctuate from A to B, B to C, so on, but because I have assumed the energies to be the same, it does not absorb or emit any energy. But thermal fluctuations do induce transitions among these metastable states. Yeah. Okay. So, to answer your question, if the energies of these three states were different, then sometimes it will absorb energy and sometimes it will emit energy to the reservoir.
I don't know how important this is, but if you think of really turning on an interaction that will break the BJT system. So in the end, the ground state will be 0 plus 1 and the other one will be 0 minus 1. So presumably this is not very important for you that the energies are the same. Because
It's not very important.
this interaction will break the degeneracy.
Yeah. And if, as you said, I mean, even initially I could have assumed that the energies of the three states are different, only that will complicate the algebra, that's it. Okay. Yeah, it's just a classical system, nothing quantum here. Yeah. I mean, people have done quantum analogs of similar systems, not exactly the same system, but the essential idea behind the Maxwell's daemon is not dependent on quantum features. Okay. The essential idea can be described also in terms of classical systems. Yeah. Okay. With that, I make the following claim. Yeah.
Why do you need three-state daemon?
That's a good question. Why 3 state? So think I want a circular rotation. Okay. If there are only 2 states, I need to have 2 parallel modes of transitions or 2 channels, so that it goes through one channel and comes back via other channel. Yeah, so that there is a circular motion, but that's a little difficult to visualize. So that's why I had 3 states, and hence I can visualize, you know, clockwise or counterclockwise rotations. That's precisely the reason. Yeah. So I make the claim that if all the incoming bits are in state 0, on the average, the demon will perform clockwise rotation. Okay, which says that thermal fluctuations, which are evenly distributed among positive and negative values, have somehow been rectified, because I now have a directed motion. Okay. So there is an easy way to see it, and that's the following. Remember the transition rules we had, that the demon can go directly from C to A if the bit flips from 0 to 1. Okay. Now, via this rule, if all the incoming bits are in state 0, there cannot be any transition from A to C on the average, right? I mean, there can if the bit flips from 0 to 1 and then goes back, but after the whole interaction is over, there cannot be any net transition from A to C, because all the bits started in state 0. Okay. So there are only 2 possibilities. There is no rotation, and if there is any rotation, it's in the clockwise direction, right? And because that is so, on the average, we do expect an average clockwise rotation for the demon, and that's how we get the thermal fluctuations of the reservoir rectified. I hope that point is somewhat clear. All it says is that counterclockwise rotations are not allowed because all the demons are initiated in state 0. There are only 2 possibilities, no rotation or rotation in the clockwise direction, and hence we expect that on the average there will be clockwise rotations, okay, of the 2 possibilities. So there will be some bits for which there is no rotation, but that's fine. I'm talking about average number of rotations per bit. Now, pictorially we can see it in the following way. Consider the moment where the demon is in state B, and the nearest bit, which I have put in shade here, is in state 1, okay, via interaction or something. At the next moment, the new bit becomes the closest to the demon, so that the demon starts interacting with this bit. Due to intrinsic fluctuations, the demon can go from B to C, right, while still interacting with that nth bit. And at the next moment, because of the combined transition rule, the bit can flip from 0 to 1, and simultaneously the demon can go from C to A. That's allowed. And finally, because of its own thermal fluctuations, the demon can go back to state B. So that's how we can have a clockwise rotation if the initial bit is in state 0, right? So I wanted to give this physical picture to see how we can obtain a clockwise rotation in general. Okay.
What is the relationship between the rate of this intrinsic change and the speed of this? I mean, if the rate is fast, then you could have this back and forth motion.
Yeah, there will be back and forth motion. So if you look at the fluctuations about the average motion, they will be larger. Yeah. So in the following, we will refer to some exact formulae, but mostly they are about the average behavior, not the fluctuations.
But do you assume anything about the rate of these changes versus V and V?
Yeah. So in the following, I assume that these rates are all unity. So that defines the time scale, and then I define generic V and D and everything.
Oh, so you don't assume tau greater than 1 or less than?
I do. So I assume these intrinsic rates where transitions are along the continuous lines, them to be unity.
I understand. But what is tau?
Tau is the interaction time.
I know.
Yeah.
I'm just asking whether you set it to be greater than 1 or less than 1 a priori?
There is no a priori setting. They can be anything. Yeah. Okay. And once there is rotation, I can assume that I can attach a tiny mass which goes up if the demon rotates clockwise, right? And if the mass is small enough, this finite rate of rotation should not cease. And hence, on the average, we do expect that the demon will go on rotating clockwise, the mass will be raised, and hence will be extracting energy from the reservoir and converting it into work, just like Maxwell's demon. Okay. With that picture in mind, let me attach the mass. Okay. And as I said, whenever the demon goes from C to A, thus trying to complete a clockwise rotation, the mass goes up by a certain amount, I call delta H, and the mass itself is given the value of small m. Okay. And note that this movement of the mass is associated with the combined transition of the demon and the bit. Okay. Fine.
So here nothing seems to depend on the thermal fluctuations. It's all about the interaction between the bit and the demon. So why do you say that?
Thermal fluctuations? Well, unless there are thermal fluctuations, the system will not evolve. It is possible, right? So thermal fluctuations provide the mobility, so to speak, to make transitions from one state to another.
So this delta H energy is absorbed from the reservoir?
Yeah, because there is no other source of energy, right? Because both the states of the bit are the same, do have the same energy. So the energy cannot come from the bit. All the states of the demon have the same energy, so it cannot come from the demon either, and hence it has to come from the reservoir. Yeah. Okay.
But you're not violating the second law in some sense because you are doing work in pulling the damn thing.
So there is no, you see, I mean, this motion is vertical, right? Whereas the pulling happens at a constant speed, and there is no coupling actually.
Someone has to do it.
Okay, so one way to visualize is the following. You can attach a heavy object which moves at a constant speed, and then attach the stream of bits or the tip of bits, so to speak, with it. And you can okay, I know, I do get this question very often, but all I can say is the following. This movement is in the horizontal direction. This movement is in the vertical direction. Even if I pull it with a certain force, that force will do no work for vertical displacements. Sort of. So at the end of the day, I will show you a video which is much more mechanical than this schematic picture, and there you can see that there is no coupling. Okay.
So you're claiming that there is a violation of the second law? I would say this is a non-equilibrium system. And then
This is non-equilibrium system.
one does not really.
No, second law applies to any transitions, equilibrium or non-equilibrium. That doesn't respect any. The rates satisfy Dittel balance. So long as that happens, I am not violating anything. I mean, I can write down the rates. For presentation purpose, I have taken them off, but I will present them towards the end.
The rate of entropy increase is always greater than the other way around. I mean, that is always satisfied even in non-equilibrium.
Yes, that's what I said. That second law is valid no matter whether it's equilibrium or non-equilibrium. Yeah. And also, I do not require all the incoming bits to be 0. They can be different mixtures of zeros and ones. Only for the sake of analysis in the following, I assume that the bits are uncorrelated. Okay? So they are statistically independent. And P0, P1 denote the proportion of incoming bits, which are in states 0 and 1 respectively. And similarly, P prime 0 and 1 denote the proportion of bits in state 0 and 1 in the outgoing stream. Okay? That's just a notation. With that, I will try to present the results, but before we go to the results, I would like to say a few things about information entropy. I know it's like preaching to the choir, but for the sake of completeness, let me just say it. Okay? So for information entropy, I mean the Shannon entropy, which I have defined here by H, simple P log P. Okay? And for a two-state system, we can show that it lies within this interval. And then if this entropy is 0, that means the bits are definitely in state 0 or definitely in state 1, which means that they are blank because I know a priori in which state they are in, and hence there is no information there. If, however, the information entropy has the maximal value, we can show that that situation corresponds to having equal number of zeros and ones on the average in the stream of bits. Okay. And finally, by change of information per bit, I mean the following. It is simply the difference of the information content of the outgoing bits minus the information content of the incoming bits. Okay. So, that is the change in information in the bits. Okay. Now, what are the parameters that are relevant for the system? First is the excess proportion of zeros. Zeros are important because we have seen that if all the incoming bits are in state 0, there is work performed, and that is why we can assume why this parameter is important, and I call it delta. Then epsilon is just a rescaled mass, you might think. Okay. And finally, tau, the interaction time. This is the time during which the daemon interacts with a single bit. Okay. And what are the quantities we are interested in? First, the average rotation per bit. Okay. How many times does the daemon rotate in the clockwise rotation per bit? Okay. And once we know that, we denote that by phi. Once we know phi, we can calculate the rate of work done. It is simply proportional to the rotation rate. And finally, we can also calculate the change in information using the formula I will show in the next slide. Okay. So, here is the result. I have phi, the rate of clockwise rotation per bit, in terms of the 3 parameters of the system. Okay. The algebra is a little complicated, but that should not worry us. All you need to see is the following, that the current is a factor of 2 terms. First term is simply a difference of the 2 parameters delta and epsilon, and the second quantity, a complicated function of the other parameters, is non-negative. Okay. These are the only 2 features we should keep in mind, which says that the sign of phi is the same as the sign of this difference, delta minus epsilon. That is the only feature we will need in the following. And of course, if we know phi, we can calculate the average work done and also the change in information per bit using this formula. Okay. Yeah. So, delta is the excess proportion of zeros. Epsilon you can think of as a rescaled mass or weight, and tau is the interaction time with each bit.
So this bit stream is a predetermined bit stream or?
Statistically. So, I know that P0 proportion of the bits are in state 0 and P1 of them are in state 1, and also that there is no correlation, they are statistically uncorrelated. Only that much information I know. Yeah. Okay. So, now before we go into pictorial descriptions of the results, let me just give you a notion which will help us in understanding the behavior of the system. As I said, because the second factor eta is non-negative, sign of this current is the same as the sign of this difference. And then you might say that there are actually 2 effective forces at play. First is delta, the excess proportion of zeros, which tries to induce clockwise rotation. We have seen that. And second is the gravitational force, where the mass tries to go down and in the process tries to induce counterclockwise rotation. And it is the interplay between these 2 forces that determines the behavior of the model. Okay. With that, let us go to the so-called non-equilibrium phase diagram of the system, and by that I mean the behavior of the system as a function of different parameters. So, on the x axis here we have the excess proportion of zeros or delta. On the vertical axis we have the rescaled mass or epsilon, and here I have demarcated some regions. Okay. Let us go to these regions one by one. First, let us consider the region I have marked by engine. This is the region where we can see from the formulae that the rate of work done by the daemon is positive. Okay. And in a way, this is easy to understand. Why? Because in this region, we see that the delta force, which tries to induce clockwise rotation, is greater than the epsilon force, right? As a result, we expect that there will be a clockwise rotation, and hence the mass will go up, and hence positive work will be performed on the average. Okay. Let us then go to the second region, which I have marked by eraser, and by eraser I mean the following. The information content of the bits, which are measured by the Shannon entropy, decreases. So, delta SB, which we have defined earlier, is negative in these regions. And this too is somewhat easier to understand, because in this case we see that the epsilon force, where the weight tries to come down and induce a counterclockwise rotation in the demon is greater than the delta force, which tries to induce clockwise rotation, as a result of which the mass comes down and all the bits tries to go into state 1 because of the interaction rule. And hence, the information content of the bits goes towards 0 because I know with greater probability that all of the bits are going towards unity. Okay, it's like resetting the bits. And this region is slightly more complicated than the engine region, and here comes the fact that tau can be different. So, in all these previous pictures, you might have noticed that I have taken tau to be unity, but I can take tau to be anything, as I said. So, if we take larger and larger tau, we can see from the formulae that this region gradually increases until it hits this cross diagonal line. Okay. So, when tau tends to infinity, this erasure region is from minus 1 comma 1 to 1 comma minus 1, sorry. It covers the whole region. And when tau is very small, this region, the erasure region is within the vertical line and this diagonal. Okay. So, it gradually moves towards the left. Fine. And now to the second law, because we had this question, what happens to the second law? Is it true or is it false? Okay. Now, again from the dynamics or from the formulae directly, one can show this inequality. The change in information content in the bits minus the rate of work done over the temperature, that is greater than or equal to 0. Okay. That does not say very much, unless we notice that, well, this term is nothing but the change in entropy of the reservoir, because the energy to do work comes from the reservoir. So, the work we do is same as the heat that I have extracted from the reservoir, and hence this term must be the change in entropy of the reservoir. So, I can rewrite this inequality in this more suggestive form, which says that change in information content of the bits plus the change in the thermodynamic entropy of the reservoir, that is non-negative. Okay. And that answers the question as to what happens to the second law. It says that in presence of information processing degrees of freedom, it is not just the thermodynamic entropy that we should worry about, it is also the information entropy of the information carrying degrees of freedom. And when we add the two types of entropies, that total entropy can never decrease. So, that is what this means. Okay. In a way, you might call it modified second law, but or the second law adapted to this situation. Okay. But this is a generic feature of all models of Maxwell's demon, that on top of the regular thermodynamic component, we have an information theoretic term, typically Shannon entropy type term. Okay. And now we can go back to each region and see how things happen. In the engine region, work is positive, so energy is extracted, but more amount of entropy is created in the bits, and hence that is allowed. And similarly, we can go to each regions of eraser and dot and see that the sum is actually positive for each cases. Okay. So, whenever there is a decrease in some quantity, say in the information content, there must be an increase in the other quantity, say in the thermodynamic entropy of the reservoir. They balance each other. Okay. And with that, I should come back to my original curious observation, right? We started with the idea that why not extract energy from the atmosphere, right, because it has so much energy. Well, this discussion tells us that we can, but we have to have blank memories where I can write information, so that its entropy increases, which in turn allows decreasing entropy elsewhere. Okay. But a simple calculation shows that just to heat 1 gram of water by a single degree Celsius, we need 200 million terabytes of data. Okay. And what is the largest hard disk can we get? Terabyte? Exa? Even then, I mean, this is too large for that. So, you can see that even though this seems to be a theoretical solution, technologically it does not seem to be feasible.
Yeah. Is it a theoretical solution because even to write that information you need energy, right?
There comes the measurement part. Charles Bennett did suggest an apparatus where we can make measurement and write information without needing energy. at least in a limiting case. So, we believe that there are situations where without requiring any energy we can encode information, and it is only in the eraser part that we need to
Idiomatic writing, no?
No, I took the tau to be anything, right?
Yeah, but in this case, if you want to write in a way without using any energy.
Oh, right, it has to be. So, if you want to be very efficient, it has to be very slow, okay.
How does that compare with the Poincare recurrence time with this gram of water events,
These are basically discrete state systems. Poincare recurrence time, because I have taken the rates to be unity, they are also of the order of unity. I mean, you can assume, right, these are just 3 state systems, and each transition takes about 1 unit of time. So, the recurrence time is also about unity.
But then this measurement thing is actually important, right? You can't write fast enough. If you want to, if you want to really work within some realistic thing, you can't write slowly enough to consume no energy. It may be relevant, because you have to write really slowly, and then your
To
gram
be
of water may not
most
exist any longer.
efficient.
Yeah.
Yes.
to-
But there is a trade-off actually. If you do it very slowly, the power goes down, right? But if you want the power to be large, you have to do it very fast. But in that case, you are not very efficient. So there is a trade-off there. Yeah. Yeah. Yes. If simultaneously I increase the information entropy somewhere. Not in the common sense or the conventional sense. Yeah.
You were saying that this is not thermodynamic entropy, at made it pointed that you can even write information using as small energy as you like. So we are saying that entropy can be reduced.
Yeah. But as I said,
Long enough, the entropy will reduce. If you wait long enough, entropy will reduce. Second order field.
Yeah, because of Poincare recurrence. Is it same
Not
as
just
that?
Poincare recurrence, that's an extreme scenario. Anyway, entropy might reduce because you'll get fluctuations. So if you're going to write without any loss of energy in a way to increase the information entropy, you might have to wait long enough that it's not so surprising.
Yeah, but can we have a limit where we can meaningfully reduce entropy much faster than what we would expect from general fluctuation that entropy may get reduced to something?
Yeah, that's an interesting question. I don't know.
so
I would
this
think
could
that-
be an answer that you have to couple the system to an information carrying degree of freedom and let them react, so that you do reduce the thermodynamic entropy at the cost of information entropy in the other degrees. So that would be one way.
So you have to write it fast enough.
You have to write it faster.
In a natural way. If you write it so that the entropy is reducing much faster than you would expect anyway happens sometimes because of fluctuations.
You have to play with the rate parameters. I mean, if we have the means, in a closed system, okay. Yeah, but okay, but there is a heat reservoir though. Are you allowing reserve? Oh, yeah, that's fine then. Yeah. So what I'm just saying is the following, without going into rates and what time it takes to write the information. So long as this first term is positive, I can have the second term negative. That's all I meant. So it is possible, and that was the purpose of whole discussion, that we can think of physical systems, at least in principle, which does reduce the thermodynamic entropy. And this inequality just says that. Yeah. Okay.
And it did not thermalize. It did not. It could not thermalize because of the infinite energy barrier and so on.
Right.
Right. So it cannot dynamically thermalize. Now the thing is that is a very special initial state. Any typical state chosen from at that temperature would not be an all one state.
Exactly.
So you need special preparation procedure to ensure such a
Exactly.
long range order.
Exactly.
That does not have any energy cost or anything of that sort.
That's the whole point, precisely, right? That's what Landauer's principle says, that, or the whole discussion says that you need to have a dependable spatial initial state, a blank memory, right, which is a very special initial condition, that all the bits are in state 0 or in state 1. If you take an arbitrary memory, in general there will be much information in it and not all the bits will be in state 0 or 1. in which case you have to erase the memory, but in the process, because of Landauer's principle, dissipate heat. So, yes, there is no free lunch, if that is what you mean, that if you go in nature and pick up any system, it will not be in that special initial condition where all the bits are in state 1 or in state 0. No, you have to expend energy to get that fuel. Yeah. That is precisely the point of view, and this goes the other way around. I mean, it is possible that delta SB is negative and this is positive, whatever. So, in fact, that is what you are saying, that you take a generic initial condition for which the information content is very high. You want to erase the memory so that information content is very low. So, delta SB is negative actually in your case, and then it says that delta S reservoir has to be positive, which means there is a penalty. You have to increase the entropy of the reservoir to generate that special initial condition. So, yeah, that is also contained in it. Not really energy. I would like to think in terms of entropy.
And why erasing needs some?
Because one view is the following. Before erasing, the system has more freedom to move in its phase space. What do we mean by that? So, one way to represent a two-state system is the following. Let us have a box and a single particle in the box. If the particle is in the left half of the box, I will call it state 0. If in the right, I will call it state 1. Okay. A generic particle in the box is unpredictable, it can be anywhere. However, if you want the particle to be constrained in the left half of the box, you see that its degree of freedom has reduced, and in the process you have to basically compress the gas. Okay. You have to do work. So, that is one point of view from dynamical systems, that to erase you have to reduce the degree of freedom of the system, and that is why you have this penalty, that you have to increase the entropy somewhere else. So, in the example I just gave, when you do work, you are putting in energy, but because the particle is isothermally connected to the reservoir, it cannot absorb that energy. So, where does it go? It goes to the reservoir, and hence while compressing the one particle gas, you have actually put in heat into the reservoir and hence increased its entropy. So, here is the picture most people have. If you try to reduce the degree of freedom, somewhere else you have to pay the penalty, because systems try to occupy the largest phase space that they can occupy. If you try to reduce that, there is a penalty. Whereas free expansion, for example, does not have any entropy cost, right. So, there I think the asymmetry comes in, that you can increase the phase space without any energetic cost or anything, but if you try to reduce the phase space volume, there is a penalty. Okay. Yeah, sure.
So, where does your model precisely differ from the kind of arrangement that Feynman gives in his book on Ratchet and Paul?
Right, right.
So, where does your
Sure. Ratchet and Paul has two reservoirs, right. The two boxes have two different temperatures, and he showed that if the temperatures are the same, it does not work.
Exactly.
Right. In this case, there is only one reservoir, and still it works.
Yeah, so that's my
Yeah.
my question, that
Yeah.
in his arrangement, when the two reservoirs are at the same temperature, it doesn't work.
Right.
In your case, it's working. So, where is the precise difference
Because
coming?
he didn't have any information carrying degree of freedom. He didn't have any bits, so to speak. So, we can cook up in principle a hybrid model of Feynman's Ratchet and Paul and bits, which will precisely do the same thing, yeah, even when the temperatures are the same. And that was, I think, my last slide. Yeah, sorry. Any more questions? Yeah.
So, I guess if one looks at the tape in a more microscopic way, then probably one can again think of it really as thermodynamic entropy, right? I mean, one
Right.
can understand in terms. So maybe is this just a more efficient way of presenting it, like calling it information entropy instead of just the usual thermodynamic entropy?
Yeah, I completely agree. I mean, all through I have satisfied the regular rules of kinetics and detail balance, and the model that I have presented just shows how the daemon might work. So, it is a thermodynamic system. We have not incorporated anything which is not present in regular thermodynamics and chemical kinetics or anything. However, this is a special arrangement which explicitly points out the different features of the daemon and lets our understanding build up. So, yes, the system intrinsically is not very innovative or new. The innovation is in presenting the stuff and collecting the different degrees of freedom such a way that it meshes very well with the description of Maxwell's daemon. So, there I think is the innovation, because otherwise the kinetic rates, two states, enzyme type dynamics, these are all well known for last 150 years or even perhaps more. Yeah. Yeah.
Yeah. And if you take the tape, which has got all these information written on it, and start heating it, at some point it will randomize.
Right.
So you can think of the tape, if I don't heat it, as one more bath at 0 temperature, and yours is a machine that's doing work between the KT temperature and the tape temperature.
Yeah, that's a nice view. That's a nice view. We haven't done the exact mapping like that. So, as I said, I mean, we tend to think in the following terms, that there's a large barrier as a result of which there is no transition. But the mechanism you suggest is different, that the temperature is so low that there is no dynamics. And because we have different temperature for the bits and different temperature for the daemon, there is a transfer of heat, so to speak, and hence the work. I think that's the view I presented. I think that mapping can be done, but the way I have presented, it's not necessary. Yeah.
So effectively, replacing the second reservoir with this
In bits.
information
Yeah.
resource.
Yeah.
And making a connection between the Feynman
Yeah.
ratchet model where there were two heat baths.
Right.
Instead of that, you have one heat bath and the other, which is an information resource,
Exactly.
which is mimicking the second.
Precisely, that's the point, that instead of having a second reservoir of different temperature so that there is a heat flow, I could have information carrying degrees of freedom which are initiated in a very special initial condition, and that too acts as a thermodynamic resource. That is precisely the point. Yeah.
So if there are no other questions, let's thank Dipendu. So I just want to, sorry?
Oh yeah, of course, there is a video, of course. Okay, let me do the full screen. So this is not done by me, this is done by Jue Lu, which was my former colleague at University of Maryland. So let me first explain the things. This ring here is the daemon, okay, and these paddles are the bits. If they are inside the paper, I think here they are in state 1, and if they are outside the paper, or sorry, the the surface, then they are in state 0 or vice versa. I don't exactly remember. But if you look at close enough, so I will initiate the video, and you will see that because of thermal fluctuations, the daemon and the bits, they all fluctuate and they interact, because you see there is this protrusion from the daemon, and the paddle can collide with the protrusion and interact, as a result of which there will on the average be a counterclockwise rotation. I always forget because the fluctuations are really high. You have to look for a long time to get the net rotation.
So which is the tape?
Tape is this guy, which has all the bits. So the bits come down, interact with the daemon one by one, and then go below. Okay, let's see if it plays. So you'll see that there is a lot of fluctuation here, but I think on the average it goes in the counterclockwise direction. And as you can see that this rotation takes place in the horizontal plane. So even if there is any vertical force, that force cannot do any work on the horizontal displacements. In fact, there is the so-called etude machine. So like having two weights on both sides of the pulley, and if you make the weights the same, they can go down if you initiate with certain speed, and you don't require any energy to do that after it is initiated. You can think of connecting the bits to the etude machine, and then there is no energy given either to the bits or from the bits. I'm not sure. So could you see on it counterclockwise rotation? It fluctuates a lot. I mean, I think now it has gone at least once. So an easier way is to actually plot the time series so that I can see how it happens, but sorry, I didn't have that. So yeah, even the person who made this video, he had to look for a long time to make sure that he has done the correct thing. But this has been, I mean, other people have followed up with this particular work, with this video. They have confirmed these results with their own simulations.
Is there any experimental setup or a real experimental
So we are trying to inch towards a real experimental setup. So these are something that we are conceiving so that we become more and more realistic, and hopefully at some point we could design.
If that is 200 million, that's not very difficult because 200 million is possible measurable. You can still 1 terabyte of data, then you hit a 1 gram of water.
Yeah.
200 million doesn't should be 1 gram of water.
200 million terabytes. So 1 terabyte has 10 to the.
1 millionth of 200 millionth of a degree.
Okay.
You make the temperature change only 10 to the
You have to
minus
measure that though.
6. Yeah, so 10 to the minus 6.
Actually, yeah, I guess people can do it. Yeah. Is it Takahiro Sagawa?
Takahiro Sagawa.
Okay.
I think
Yeah.
Yeah, he actually, there's an experiment.
Actually, yeah, I should have mentioned that. There is an actual experiment, I think in Nature Physics, right? They reported in Nature Physics where they explicitly demonstrated this conversion of information into work. And the idea is actually very simple. I mean, even though it looks very, complicated or out of the world, the idea is very simple. And when Maxwell proposed his demon, he actually did so just to show that there are statistical limitations of the second law in the sense that there are always fluctuations. And if we are observant enough, we have fine enough description so that we can identify the positive fluctuations. Sorry, I don't know what they are. So that we can identify the positive energy fluctuations, we can just rectify them, right? If we are observant and fast enough.
But this is, if you associate also an entropy with the, what this distinction between thermodynamics and information entropy is a little artificial.
Yeah, in a way, but one has to be careful, and that's the following. Firstly, you cannot simply say that Shannon entropy is thermodynamic entropy. Why? Only in XP space. Coarse grain the system, and then with respect to coarse grain variables calculate Shannon entropy.
Yes.
That's not thermodynamic entropy, right?
Well, there's some S maximization procedure. So you have some sort of coarse grain variables. You take your fine grain state and S maximize with respect to your
Again,
coarse grain
that
variables, and that gives you the
that
answer.
is true only in the classical XP space.
No classical.
And also apply classical laws of motion. Shannon entropy will not change.
No, I in fact do everything quantum mechanically.
Okay.
You know,
Even quantum mechanically, the corresponding of Shannon entropy is von Neumann entropy. That will not change if you have just Schrodinger's equation, right? For a closed system.
You have to coarse grain.
You have to coarse grain, right? And
But coarse graining is okay. You
those,
always have to
okay.
coarse grain.
When you coarse grain, there is a decrease in entropy.
Decrease in entropy.
Okay, how do you? Because if you do the extremization of coarse grain, where you have just two states, so from infinite state system, you can have a two-state system.
Yes.
So the maximum entropy contained in the variable description decreases, right?
Yes.
So that is there. But on the other hand, if you have a complete description, it is deterministic, and hence there is no entropy, so to speak. But if you coarse grain, there is a stochastic description that becomes relevant, and hence you say there is entropy.
Right.
All I'm trying to say is that people
That
still.
applies also to the memory. You apply the same principles to the memory. as well.
That's what I have been doing. So when I say that there are two states, 0 and 1, these are basically coarse grained states of some finer degrees of freedom. Yes. But there are people who wouldn't agree that the Shannon entropy of coarse grained degrees of freedom should be thought of as thermodynamic entropy everywhere.
Really?
I know of many people who would say that. So that's why I try to be careful, because I don't know if they are in the audience, right? But I know of many people, even in non-equilibrium statistical mechanics community, would object to the idea that Shannon entropy of coarse-grained degrees of freedom is the thermodynamic entropy. So it's not obvious. For
So let's thank Dibendu once again. So there's a special ICTS ISC colloquium which will be in the physics department at 4 o'clock.